Today is the second class for the thermal properties of matter, or thermal energy, or total thermal topic of the A2 syllabus. In our last class, we discussed about a couple of things, and today we're going to continue from there. So in this note, for which is collected from Adnan Sami, we have the definitions for internal energy, and then we have the definition for a couple of systems. For example, what I told you in the earlier class, that if a system does some work by its own internal energy, the system experiences a decrease in internal energy. So this is sometimes referred to as work going out, or work is done by the system. So that works as a reduction of the internal energy of the system. And in other cases, if work is done on the system, that is said to be that the system's internal energy increases. So we say work goes in, that's also another work. In this case, work and energy are used in exchangeable expressions, so that works. One of the formula that we might have seen in our O levels is that work done on any amount of gas at under constant pressure. If we have a graph that has, let's say, pressure versus volume, and we have a graph like that for any amount of gas, or if it's undergoing a cycle of volume change of pressure volume, we can also have cycles that can look like this. There are many names of this type of cycles, but at any point, if we multiply these two variables, have a look at this one, pressure and volume, just for the sake of curiosity. If I multiply these two variables, what unit possibly could we get? Pressure is given by Pascal and volume is given by meter cube. So if I go ahead and divide this, we're gonna get Newton per meter square multiplied by meter cube, which ultimately results in Newton meter, which basically is joule. The point that I'm trying to show you, that the area under the PV graph actually gives us energy. So whenever there is a certain change of pressure and volume for a certain situation, the area under the graph can give you an expression of how much energy is involved for this process. Now, in some cases, we might have energy increase. In some cases, we might have energy decrease. It all comes down to the point that what is the change of cycle. For example, if we have a cycle like that, I mean, whenever I say cycle, I mean that, let's say we have a system of gas that is contained within a cylinder, and we are changing the pressure and volume situations of this gas slowly. So let's say this is our state number 1, 2, 3, and 4. If the cycle goes on like this, 1, 2, 3, and 4, then this essentially goes on to show you, you should understand that whenever we have pressure and volume, which both of which are multiplied, so if we want to increase the energy, either of them should have a bigger ratio based increase compared to the other one, or both of them might be increasing. So in this case, what we can essentially say, that for the process of 1 to 2 and 2 to 3, we're going to have an increase of internal energy. In the process of 3 to 4 and 4 to 1, we're going to have a decrease of internal energy. So by finding out the area under the PV graph, we can calculate how much energy change is happening to a certain system. However, for most part of your syllabus, you don't have that process, because in many cases these things are actually not straight lines. For many of the thermodynamic processes, these things are actually curves, which might require integration under the integration for the designated equation, which is not elaborately entertained in our A2 syllabus. But if they are straight lines, we can go for the Trapezium rule, which is pretty simple. The mathematical formula that is often used for your syllabus is that work done on a gas under constant pressure is given by P into delta V. So I can write this as W equals to P into delta V. Now, one thing that you need to understand, this is a very basic mathematical expression. Now, I have used the word work done on the system. This would mean that work is going into the material. This would mean if this delta V is expressed as V2 minus V1, in this case, or I could write also V final minus V initial. This would mean that the change of volume, which is happening over here, that should be, the final volume should be smaller and the initial volume should be bigger. What do I mean by this is something like that. For example, let's say How can I show you this? Oh, let's say we have a piston cylinder system over here. This is a cylinder which has some gas entrapped within, and this is a frictionless piston, and the piston has an arm over here. Let's say initial volume is vi, and then we're going to apply some force over here, and that is going to push in the cylinder, let's say up to this new position. So this new smaller volume, which is going to be this much, let's say this is vf. So whenever the volume of gas is getting squashed, we have to provide some energy from the outside to bring the particles closer to each other, and that works out as energy stored within the system. In this case, if delta v, I mean, if your initial volume is bigger and final volume is smaller, it means work was done on the system. That's the part that I wanted to understand. In most cases, the delta expression is always written as vf minus v1. So if vf is smaller than vi, which would lead to delta v equals to negative in typical cases, this means work done on the system. Mathematically, that would also lead to the expression of w equals to p into delta v to be negative. But in many cases for Joule calculation, we don't bother for the negative sign. We already go for the magnitude because this is a scalar quantity. But the point that I need you to remember that gas getting squashed by the application of an external force means work was done on the system, internal energy increases, and the other one is the other one. Which brings us to the next topic of discussion, which is the first law of thermodynamics. Before I go for the first law of thermodynamics, I'm going to first tell you the zeroth law of thermodynamics, which sounds a bit weird. What is zeroth law? I mean, is that even a law? Yes, the zeroth law of thermodynamics is basically a very simple concept, but it was defined as a law because scientists wanted to get this thing defined. The zeroth law of thermodynamics goes like this. If the temperature of a certain object A is equal to the temperature of a certain object B, and if the temperature of the object B is equal to the temperature of object C, then first zeroth law of thermodynamics says then the temperature of object A and temperature of object C should also be equal. Now, this might seem pretty weird. I mean, that's obvious. Well, that's obvious because you have been taught so, but that is actually based upon the idea of zeroth law of thermodynamics. I use the term temperature for this expression because it is easier to grasp and understand, but the scientists actually use a different set of word, which is called thermal equilibrium. The word thermal equilibrium basically means two objects having same temperature. If they have same temperature, we call them to be in thermal equilibrium. If they do not have any temperature, if they are not at the same temperature, we say they are not in thermal equilibrium. The word thermal equilibrium basically gives us the idea that if we bring two objects in thermal contact means a type of connection between two objects where they can exchange thermal energy. That exchange might happen in the process of conduction. It can happen in convection. It can also happen in radiation. By any means, or whatever that is involved for the relevant example. Whenever we will bring two different objects in thermal contact with each other, if they do not exchange heat with each other, that's one way to say it. Or if the rate of heat exchange is equal. If you wonder what does that mean, this actually means sort of like it can be a totally zero heat transfer, that is also possible, or the rate of heat transfer from and to each other is also equal, which is basically like a similar situation like the equilibrium state of a reversible equation. Do you guys know what that is? The equilibrium state of a reversible reaction. I mean, the reaction actually didn't stop, but it has the same rate of forward reaction and reverse reaction. So you have the concentration of the reactants and the products perfectly maintained at the same state. That's what you call equilibrium point for a reversible reaction. So if that also happens, I mean, if we bring two objects close to each other in thermal contact, and if the rate of heat transfer is equal, which means practically they are not having an overall increase or decrease of their own heat energy, we would say those two objects to be in thermal equilibrium. That's the concept for thermal equilibrium. So the actual Zeroth Law of Thermodynamics actually said in this manner: if object A is in thermal equilibrium with object B, and if object B is in thermal equilibrium with object C, then object A and object C are also in thermal equilibrium. So I just replace the word temperature with that with the phrase thermal equilibrium, because that's how it was mentioned. That's a pretty important bit. And one thing we also need to understand, not understand actually, we have to remember from our O levels, is that heat energy always flows from hot objects to cold objects. This is very important. Heat energy will always flow from hot objects, high temperature objects, to cold objects, low temperature objects. And there is absolutely no exception of that, none whatsoever. Many of you might feel like that, if that's true, then how does a refrigerator work? I mean, how does the key idea for refrigeration is that inside we have cold temperature, outside we have hot atmosphere. So and this thing works. The reason this thing works is because that this is what we call a heat pump. We actually use a certain heat transfer material, which is sometimes called the freon, or actually it can be used as the refrigerant liquid, which actually absorbs the heat from inside the refrigerator and becomes gas in the process of boiling within a certain closed metal channel. We call them evaporator within this thing, and then that gas is taken outside of this refrigerator, and some electrical pump squeezes that gas within another large amount of pipe, which is called the condenser, which is basically the part outside the fridge that becomes hot if you touch it. And whenever they are squeezed together, the internal energy stored within the gas, which they picked up from the inside of the refrigerator, they actually expressed as heat energy. So their temperature then, by squeezing them very fast, not necessarily very fast, by squeezing them, the temperature of that gaseous substance becomes hot enough. So they becomes warmer than the atmosphere, and as a result, they start to dissipate their heat energy to the atmosphere. So the total amount of internal energy for a fixed amount of gas becomes lowered. And eventually when they are once again, so in this process, they are made into liquid by Joule-Thomson effect. That's also another thing. You don't have to know about that. And eventually when the liquid refrigerant is introduced back into the refrigerator box, they once again are allowed to evaporate, and in the process of evaporate, they absorb the latent heat of vaporization from the inside, and this cycle keeps on happening. To make this process happen, we have to keep on running the pump that is responsible to cause the the refrigerant fluid, gas or liquid, that has to move within the closed cycle. So it's not essentially natural that heat energy will automatically flow from cold object to heat object. If you want to do that, you can do that. You have to spend some physical work in that process, but that also within that process, that logic will also follow the simple rule that heat will always flow from hot objects to cold objects, high temperature to low temperature objects, and that there is no exception for that. The first law of thermodynamics can be written in a lot of different ways. I'm gonna show you. Yes.
Our exceptions have one we animals, because like I'm really colder environmental থাকে আমাদের তো body temperature constantly থাকে.
Oh yeah, বলতেছি. The reason our body temperature remains constant is because our biological systems, we are warm-blooded animals. Warm-blooded animals means that our biological systems are tuned to operate at a specific temperature range. So for example, for us human being, the temperature is about 98.4 degrees Fahrenheit, or nearly 37 degrees Celsius, about 37 degrees Celsius. That's the temperature that our body functions at. So our body has some internal mechanism by which it can maintain that temperature by burning chemical energy that is stored within our body in liver, or in glucose, or in our fats, or in our muscles. It will regulate the heat generation of our body so that that temperature is maintained, which means that this is very simple. The way it works is that it actually can squeeze the capillaries of the blood vessels in different parts of our skin, and that squeezing can increase that can control the evaporation rate. So practically speaking, we are pretty much always, I mean, let's say I'm in Bangladesh. So the temperature of the atmosphere is, let's say, currently 30 degrees Celsius. My body is at 37 degrees Celsius, which means my body would tend to lose heat to the atmosphere. That losing heat keeps on happening from my body, and my body keeps on producing that heat from its energy sources. This is one of the reasons that we have to continuously feed. Our body needs food because we have to continuously maintain the temperature. Then again, if you think that if I go to some other hot country, for example, some desert area in Africa or in Middle East or Australia, those places, let's say the temperature of the atmosphere at a certain midday level is, let's say, 50 degrees Celsius, and my body temperature is 37 degrees Celsius. In that case, heat energy will try to get within into my body. Now, in that case, my body should be working in such a way that heat should not get into my body. My body will try to produce some cooling effect. Now, our body necessarily is not designed to produce of its own cooling. It's designed to have its own evaporation. I mean, our body is designed to lose heat by means of evaporation from the porous skin. What they're called? Those. It's not spiracle. I forgot the name. যেখান থেকে ঘাম শুকায় যায়, এগুলার জানি কি বলে, স্কিনের নিচে যে ফুটাগুলো থাকে।
I forgot to.
I forgot the name. Anyway, so epidermal যে হোলগুলো থেকে আমাদের the epidermal holes which actually allows the sweat to evaporate out, that evaporation process actually lets our body to become cool down, and we are always in a state of cooling, and whenever this cool down happens pretty rapidly, we feel the sense of comfort. So it basically means that whenever our body loses heat pretty fast, we feel comfort, but that comfort has a range. For example, if my body temperature is at, let's say, 37 degrees Celsius, if I maintain the AC of my room as at maybe 20 degrees Celsius or 22 degrees Celsius, I'm gonna say it's a comfortable temperature, because that's what that's the environmental climate that I was born into. But the question that you asked, that how does our body regulate the temperature? Our body always tries to maintain a fixed amount of temperature for its own internal functions. If it cannot do that, our body will undergo some shock. For example, if it becomes too cold, the situation that we call hypothermia is that if the cooling rate of our body is much bigger, significantly bigger compared to the heating effect that our body can produce, then the total temperature, overall temperature of the body is going to slowly become smaller, and that can lead to a scenario called frostbite if it's for a localized region, and if it's for the core temperature falls below a certain level, we call it hypothermia. So our body is designed to operate at a fixed temperature. I'm not sure if that answered your question, but did it answer your question?
Yes, sir. আমি just ওইটা বলছিলাম যে আমাদের তো বডি রেগুলেশন করে না, থার্মোরেগুলেশন, তো এই জন্য তো আমরা তো লাইক একটা এক্সেপশন হব নাকি, সেটার কথা বলতেছিলাম।
We will not be the exception. Our body also works in the law, under the law of thermodynamics, is that if the temperature of the atmosphere is too low compared to our body temperature, it will produce more heat to maintain 37 degrees Celsius. If the temperature of the outside is too high compared to our body temperature, our body will try to not accept heat. So we have to use thick shields or thermal shields so that our body is not exposed to that hot temperature as much as possible. So that also happens, but will not be an exception. Okay.
All right, sir. Thank you, sir.
Sure. The next thing that we're going to discuss is the first law of thermodynamics. First law of thermodynamics can be written in two different ways. I'm going to tell you both of them. Dynamics. First law of thermodynamics. Okay. Before I get into that, let me just find out the expression that you have in your textbooks. So I'm going to pause the recording a bit. Okay. Course book, say course book second edition for A levels, and the expression that we have in this book for the first law of thermodynamics, it's given like in this format. Increase in internal energy is equal to energy supplied by heating plus energy supplied by doing work. Try to understand. If you want to increase the internal energy of a certain amount of gas, we should write that as delta U. In this case, we have used the term increase, which means we are trying to increase the internal energy. That can be done in two different ways. We can either provide directly heat energy to the system, energy supplied by heating, or we can do energy supplied by doing work, which means if we do some work on the gaseous system by reducing its volume, by squeezing it, so that can be also stores, that process can also store some internal energy within the system. So these two things are written as del U equals to Q plus W. This is known as the first law of thermodynamics. This is the common expression that you have in your syllabus. There is another different version of it in some other textbooks. You might find this. This is one of the versions that I came to learn when I was learning this part, is that the amount of heat energy that is supplied to a certain amount of gas can be used in two different ways. It can be used as change in internal energy, and also be used as the work done by the gas. Now you might wonder, what is happening? Why do we have two different formulas? So I'm going to write the textbook formula over here. The textbook formula says delta U equals to Q plus W. Be very careful to listen to the description of these variables. Increase in internal energy equals to heat supplied to the gas plus work done on the gas. This is very important. Work done on the gas means energy is fed into the gas. This expression that I've written over here is basically heat supplied to the gas equals to increase in internal energy plus work done by the gas. So what this is telling us, that if we have a certain amount of gas within a container, if you apply some heat over here, naturally what can happen, the gas is going to heat up a little bit, and the gas amount is going to expand a little bit as well. Whenever the gas will expand a little bit, it will do some work against the atmospheric particles. So some work will be done by the gas that stored that was fed the heat energy. So in this case, delta W was described as work done by the gas. So these are not the same thing. On the gas means energy is going in, by the gas means energy is going out. To tell you the truth, both of these formula practically mean the same thing. Let me show you how. If I keep the delta U on the same side and take the delta W on the other side, I can also write this thing. Have a look. Delta U equals to Q minus delta W. So if I write this equation, which I'm just trying to make it similar to this, so I'm trying to show you the comparison of these two expressions. So whenever I'm given the minus sign, this should be heat energy supplied to the gas and work done by the gas. So what work is going out. If you just make this minus sign plus, you can reread this as heat energy is supplied to the gas plus delta W, which can be written as work done on the gas. So it's basically the sign of plus and minus. If you are considering this format, you have to understand that the total amount of internal energy increase can be done by two methods: heat energy supplied and also doing some physical work on the gas. If you consider this expression, you can understand this thing as that total amount of heat energy, if any amount of heat energy is supplied to a certain amount of gas or system, some part can be used to increase the internal energy, and another portion will be used to do some work on the environment or on the surroundings. So some amount of energy would be, some amount of heat energy will not be used for increase of internal energy. Both of the equations are perfectly all right. Both of the equations can come in handy in different scenarios, and we're going to see multiple different applications of this formula pretty soon. This is the key idea of first of thermodynamics. First of thermodynamics is basically built upon the concept of conservation of energy. It simply means that energy cannot be created or destroyed, can only converted from one form to another form. So if we are supplying some heat energy to a certain system, although we might not be able to detect all of that supplied energy within the system, the energy simply doesn't get destroyed. It could also be located elsewhere. It could be located somewhere else, which we have to, if we look out for it, we should be able to find. So that's the first of thermodynamics. There is some pretty interesting math that goes on for first of thermodynamics. We'll see about those after a while. The next thing that we have over here, for example, we have some examples over here for the case of average K. Let's have a look at the class note. Okay, this paragraph is a very basic description. This is a pretty interesting paragraph for us. Have a look over here. Average K of particles is proportional to temperature and increased P is stored when the particles achieve greater separation. Both of these factors can individually or simultaneously affect the internal energy of a system. Now, let me help you to understand this thing. This is pretty interesting, important paragraph. The temperature of a certain object is primarily, or you can say almost exclusively, controlled by the average kinetic energy of the particle. This word average is very important. In many cases, students miss out to write the word average and lose 1 mark. You have to understand that whenever, at any instant of time, not duration, at any instant of time, if you consider a piece of object, maybe solid, maybe liquid, maybe gas, all of the particles do not have the same speed. Some of them are moving pretty fast, some of them are moving pretty slowly. If you have, you might have come across the Boltzmann distribution in your chemistry. Did you come across that term?
Yes, sir.
There is a distribution of the speed of the gas molecules. It's called Boltzmann distribution. So point I'm trying to make is that some of the particles can move pretty fast, some of the particles can move really slow. Most of the particles will have a more or less close to average speed. So that's why you have to use the term average kinetic energy, not only kinetic energy. So average kinetic energy of the particles is directly proportional to temperature, which means it exclusively controls the expression of temperature. Whereas the stored energy or the potential energy that is stored within a certain substance is usually expressed in terms of the separation of the particles. Typically, largely separated particles have more potential energy stored within. If you wonder why, there is a reason for this, is that whenever we consider the state change of certain of regular objects, for example, from solid to liquid to gas, we always apply some heat energy to the object. So solid has to be fed some heat energy to convert it into liquid, which we call latent heat of fusion, and liquid has to be fed some energy to convert it into gas, which we call latent heat of vaporization, or boiling, sometimes we call it. So this additional amount of energy that we feed into the system when the melting or boiling happens actually helps the particle to partially or completely, partially for the solid to liquid scenario and completely for the liquid to gas scenario, partially or completely loosen up from themselves. Loosen up in this case actually is a very common term to make sense with you. The physics term that we use is we say to partially overcome or completely overcome the intermolecular forces. So the idea is that particles have some significant intermolecular attraction forces between them, significantly strong attractive intermolecular forces between them. Whenever we want to make the state change, if we apply heat to them, this is gonna cause the particles to move faster, vibrate faster, or and then they're gonna break free from their fixed structure, or they're gonna break free from their intermolecular attraction force. So in all of these processes, the particles would actually be given more intermolecular spacing in most cases, and that can lead to an increase of potential energy. We're gonna deal with quite a good number of examples in our worksheets as well. The bottom line that you need to understand that in certain thermal processes, physical processes, I mean not chemical processes, I mean if you consider physical processes, means we're gonna have mixing of materials, we're gonna have temperature mix of materials, but one compound will remain as is. We're not considering the chemical reaction over here for your syllabus at least, but in your upper level you can actually go for that. One thing that we'll always try to make sure to understand that whenever in a physical process, if an object maintains its volume, then we're going to consider the particles intermolecular spacing remains constant. If the volume of the object increases with the same amount of mass, which means with the same number of particle numbers, because mass relates to mole, which relates to the number of particles in terms of using the Avogadro's constant concept, Avogadro's constant or Avogadro's number. So if we have the same number of particles which now occupy a bigger volume, that would essentially mean that particles now have a bigger amount of potential energy, because to separate them out from their original orientation to the new orientation, we had to definitely feed them some significant amount of energy, using which they separate themselves away from each other at a higher distance. So more volume would naturally mean to an increase of potential energy. Decrease in volume would refer to a decrease in potential energy. and higher temperature would refer to an increase in the average kinetic energy. Higher lower temperature would refer to an average decrease of the kinetic energy, a decrease of the average kinetic energy. So uh, this is the couple of variables that we need to sort properly so that we can answer the questions properly. We have some examples over here. Let's have a look at the first example. For example, during evaporation, state change occurs at the same temperature. Evaporation. So let's say that atmosphere, room, everything has a fixed temperature, but you are continuously losing water molecules out of from the surface of a water body. So that's what we call evaporation. During evaporation, state change occurs at same temperature. So the water molecules which get evaporated has the same average kinetic energy as water molecules which are remaining in the container. This is because the temperature is same. Now, this is the part that you have to understand. When the state change is happening, the liquid particles and the evaporated gas particles, overall, they have the same temperature. We are talking this the ambient temperature, at the temperature of the room. So this would mean the gaseous particles and the liquid particles, they would all have the same average kinetic energy. However, in the gaseous state, the average P of the water molecules is far greater than the water molecules of the liquid state. In evaporation, intermolecular spacing got increased and work had to be done, or energy had to be provided to give them the increased separation, working against intermolecular forces. See if it makes sense. Yes, so whenever, because in the process of evaporation, the gaseous state and the liquid state pretty much has the same temperature. We'll say for both the states, the average kinetic energy of the molecules, whether they're a gaseous molecule or the liquid molecule, the average kinetic energy will be same. However, in the gaseous state, the potential energy is significantly larger. Average potential energy of the molecules, vapor molecules, is significantly larger compared to the average potential energy of the liquid state molecules, because their separation is significantly larger. That's the key idea. And then we have the concept for pressure cooker. If you have a look over here, the volume of the content remains same, so spacing cannot change. So that's a very basic idea of pressure cooker. If you have a pressure cooker, if you're boiling some materials over here, the internal volume of the pressure cooker is practically the same. You cannot have an increase of the volume because you fill up the whole upper empty space, I mean, which appear to be empty, but it's filled up with atmosphere. You fill up the entire upper space with steam, and once that air becomes 100% saturated, it can no longer accept steam further water molecules at the same temperature. So what is happening? The volume of the content remains same, so spacing cannot change. I mean, average spacing, it has to remain constant. As energy is supplied, it increases the average kinetic energy of the molecules and temperature. So within a pressure cooker, because the volume is fixed, so if you keep on applying heat, the gas simply cannot go out expanding. So as a result, the temperature has to increase. This is essentially why boiling water within a pressure cooker will take significantly shorter time compared to boiling water in an open pot. If you have an open cooking pot, maybe a saucepan, and you start to boil the water, and it will boil. If you have a significantly strong heat source, it will start to boil. The amount of, if you measure the time, that how much does it take to boil from room temperature to the boiling starting, and if you take the same amount of water within a pressure cooker and start the same process, you'll find out pressure cooker takes significantly less time. The idea is very simple. In the open cooking pot, the water could evaporate out. Much of the water could evaporate out, in which process you're losing heat energy and you're allowing the expansion. So a huge amount of energy, heat energy that you're supplying, is actually leaving from your water molecules as the potential energy of the evaporated gas molecules. Whereas if you do the same thing within your pressure cooker, those water molecules which just got evaporated cannot escape. So they are stuck within that part, within the open space of the pressure cooker above the water level. So because they cannot escape, pretty much all the heat energy that you're trying to provide will stay. Significant portion, pretty much, I should say pretty much, significantly bigger portion would stay within the water, and the boiling can happen much faster. We can actually, in any thermal process, it's almost impossible to reduce the heat loss to zero. I mean, we can never actually make the heat loss to zero, because always some heat loss will happen. If you can stop conduction, if you can stop convection, almost never we can stop. We can never stop radiation completely. If you have a heat object, it will definitely give out some infrared radiation. There is absolutely no stopping it. You can wrap it around by some silver materials or something like that, so that radiation would be minimized, but you cannot make it zero. So thermal loss is a pretty common example for most heat processes. There can be more examples over here. That's why we have number 3 and some gap over here. We're going to see more examples in our worksheets as well. So if you feel like, you can fill up this space with your own example writing. The next topic that we have over here is this one. So this is the first law of thermodynamics. Okay. Oh, next example is over here. Whenever some amount of water is heated to boil, during the boiling process, the temperature does not change, but we need to provide heat energy continuous to maintain boiling. This applied or absorbed heat energy goes into two places. Part of the heat energy is used to overcome the intermolecular attraction forces of the water molecules to make them free of each other, which is basically the gas state. To occupy volume for itself, the steam molecules have to push out atmospheric particles and do some physical work in the process. Part of the energy goes out to do this work. এই জিনিসটা খুব ভালো করে বুঝো. I'm going to draw this out for you. Let's say we have some open cooking ware. We're applying heat energy from here. Maybe this is a stove or Bunsen burner, and here we have some liquid water, and now the water is starting to boil. So we have bubbles formation, and the bubbles are going up. Now what I need you to understand that the amount of heat energy that we're providing, which is causing the boiling process to happen, is actually gonna be distributed in two different paths. The first thing, in the liquid state, the particles were really close to each other. They were clustered close to each other. So whenever they has to convert into gas, they has to become really far apart. So they have to be separated significantly further from each other. So that separation increase requires some work done. That's what one part of the heat energy supply is doing. The next thing is that, try to visualize this. When the boiling was not happening, this part was entirely filled up with atmosphere. Let's say I'm showing the atmosphere with green. When the boiling will happen, the water molecules are going to come over here in gas state. They have to push out the atmosphere and make their own space, because that's the gaseous state that you just produced out of water. So they will have to occupy their own volume, and to do that, they have to push out the atmosphere out of their path. There is pushing. Pushing means work is done. So that steam that is being produced, that steam will actually push out the atmosphere and do some physical work in that process. So supplied heat energy will be going in these two places. Have a look at these two parts once again. Part of the heat energy is used to overcome the intermolecular attraction forces of the water molecules and to make them free of each other, which is basically the gas state. So the boiling process, the main boiling process, requires some heat. To occupy the volume for itself, the steam molecules have to push out atmospheric particles and do some physical work in the process. Part of the energy goes up to do this work. So to occupy their own volume, they have to do some work as well. Average kinetic energy of the particles of a system relates to temperature. Average potential energy of particles of a system relates to intermolecular spacing. This was the third example. I think this was in another class. The third example happened in another, so that's why it was left space. And I got the notes from two different students. I don't remember whose copy was this, but it's also a good writing. This is Adnan's handwriting. I know this for sure. Anyway, thanks to the other student as well. I forgot their name, but it's helpful information. The first of thermodynamics. This law helps us to accurately calculate multiple multiple energy values of a system. I just told you that delta U equals to Q plus W. Have a look over here. Delta U over here means increase in internal energy can be done by heat supplied to the system. W is expressed as work done on the system, which means in this case both Q and W are fed into the system, both of which are attributed towards an increase of the internal energy amount. For a given gas at fixed pressure, delta W is given by pressure into delta V. Compression means work is given in, work is going in. W would be positive. Compression means work is provided. Expansion means work is going out. W would be negative. Basic level stuffs, we just discussed this. One of the stuffs we actually discussed about this part in our first class, where I told you about the triple point of water, and I told you a bit of a difference for the first and the second decimal places of the values of 0 degrees Celsius. 0 degrees Celsius temperature is 273.16 Kelvin, whereas the triple point of temperature is 273.15 Kelvin. So that's a bit of difference. Then we have the gas laws. Achha, before I get into the gas laws, any questions so far? Anyone? No. Yes? No. Achha.
No, sir.
Let's go for the gas laws. We have basically 3 gas laws. Or we can also say basically there are 2 gas laws. The Boyle's law tells us pressure proportional to 1 upon volume. So P proportional to 1 by V when temperature is constant. One of the key part for all of these gas laws to be applicable is that basically we have 3 variables: pressure, volume, and temperature. Pressure, volume, and temperature. How these 3 variables are related to each other is basically the content of the gas laws. And the gas laws are always applicable for masses or for materials which are maintained at a fixed temperature, which is applicable for a fixed amount of fixed amount of gas, which means if you are trying to observe these proportionality relationships, you cannot change the mass of your gas. I mean, you cannot inject more gas within your observable system, or you should not you should not allow some gas to leak out from your system. That's the important part. So this is actually mentioned over here for a fixed mass or mole of gas, but I should have written this over here. This is a very important precondition. So Boyle's law tells us P proportional to 1 by V when temperature constant. Trapezium law tells us V proportional to capital T. Capital T in this case represents Kelvin temperature. Very important. We cannot use degrees Celsius for these laws. Where pressure is constant, and pressure law is that pressure is proportional to temperature when P is constant. If we combine all 3 of them, we get PV by T for any fixed amount of gas, any fixed mole number of gases. The ratio of pressure into volume divided by temperature will always give us a constant. This is what we call the ideal gas equation. It's very important. Have a look at this word, ideal gas equation. You should remember that whenever we define something as ideal in physics, it primarily means it is non-existent. It's a highly simplified scenario, and it is untrue. That's what you call it to be ideal. Now, why ideal gas equation is like that, and why real gases are not like this? We're going to talk about this a bit more later. For n mole of gas, this constant is n into R. R is called the molar gas constant. Molar gas constant basically means, have a look at the definition, have a look at the unit. It would pretty much make sense just by looking at the unit. Have a look. Molar gas constant is defined as 8.31 joule per mole per Kelvin. 8.31 joule per mole per Kelvin. This basically means for 1 mole of ideal gas, if you want to increase 1 Kelvin of temperature, for 1 mole of gas, for 1 Kelvin of temperature, if you want to increase 1 Kelvin of temperature, the amount of heat energy you're going to require is 8.31 joule. So 8.31 joule per mole per Kelvin. This is somewhat similar to specific heat capacity, if you recall that property. Do you remember specific capacity? Anyone?
Yes, sir.
Specific heat capacity basic idea কি ছিল? Specific capacity formula ছিল হচ্ছে C equals to Q divided by M into delta theta. So এটা ইউনিটটা ছিল হচ্ছে joule per kg per degree Celsius, or sometimes you could also write joule per kg per Kelvin. So this is basically how much joule is required to increase the temperature of 1 kg object by 1 Kelvin. So molar gas constant is pretty much also the similar thing. Have a look. How many joules is required to increase the temperature of 1 mole gas by a temperature variation of 1 Kelvin? So that's the molar gas constant. If you have n moles of a gas, that constant is given as nr, and which basically gives us PV by T equals to nr, which ultimately leads to the equation PV equals to nRT. Whenever, if in any of your worksheet questions or A-levels questions, the question pops in that what is the ideal gas equation? This is the equation that you have to write. Ideal gas equation is that for a fixed amount of gas, for any variation of pressure, volume, temperature, the ratio PV by T will be a constant. That's the expression of ideal gas. So this is ideal gas equation. PV equals to nRT is a practical, useful version of the ideal gas equation, where we have defined that constant, and we're going to use that equation a lot of times for the upcoming discussions. So এটা হচ্ছে একটা জিনিস. So I'm going to take a small break. I'm actually parched. So then I'm going to take up this topic of root mean square, and we're going to see more about this whole thing. This is a pretty interesting thing to understand, and it's important that you understand this clearly. I'll help you to understand this thing clearly. 5 minutes. Continue the class. Root mean square velocity or speed. What do you mean by that? Now, why do we need this in the first place? Have a look over here. If the multiple gas molecules have velocities C1, C2, C3, Cn at any instant of time. Now, here's the deal that I need you to understand. If we keep a certain amount of gas within a closed container, let's say this is a container, and there we have kept some gas. Let's say the number of gas molecules within this container is n. So at any instant of time, all of these gas molecules have some movement. Let's say their individual velocities at any instant of time is C1, C2, C3, C4, Cn. If we are asked that what is the average velocity of these particles, because these particles are practically not going anywhere, they're pretty much stuck within this container. So under any amount of time, they will be within this container. They'll be bouncing off the walls, they'll be bouncing off each other. So the average velocity of the particles will at any point of time would be actually zero. I mean, if you do the vector sum of C1 plus C2 plus C3 plus plus Cn, this will be always zero because the particles don't have a resultant displacement. This might lead to the wrong conception that the particles are not moving at all, which is not the case. The particles are actually moving. So to have a measure of what their average speed is, we have to do this calculation without these vector things. So somehow we have to get rid of these vector things. And how do we do that? Is basically what you call RMS. So root means squared. So what we're going to do, first we're going to square all of these velocities, and squaring a vector quantity practically makes it scalar because it's the dot multiplication with each other. So if we first square them all, C1 square, C2 square, C3 square, sorry, C3 square, and then Cn square. We squared them all to make them scalar. We add these all and then find out the average. This is the mean. So have a look. Root, we have done the square part, then we've done the mean part, and then we do the root over part. And this is basically what we call the root mean square. Speed or velocity, however placed, that wouldn't matter because it's basically scalar quantity. But we actually squared all the individual velocities of all the gas molecules within this container at one instant of time. This is what we call the root mean velocity or root mean speed, root mean squared velocity or root mean speed. And this is represented by the symbol like this, with a less than equals with a less than and greater than symbols on two sides. This is the symbol for RMS velocity. This is a very important concept. And if we want to use the square value of this one, we simply don't do the root. That would be represented like this. For example, C square, like that. This would mean this is just the sum of the squares, and C1 square plus C2 square plus C3 square plus plus Cn squared divided by n. This is basically the mean square velocity without the root. We're going to use these two expressions to a lot of individual different parts for the upcoming calculation. Let's have a look over here. We are going to derive this formula, PV equals to 1/3 mc square. Now, this is a very important equation, and we're going to see how this works. I'm going to write up this equation. I'm going to show you this whole derivation process in detail. So, I might as well draw a new cube. So this next thing is the derivation of PV equals to 1/3 mn c square. It is very important that you have a very good look at all of these individual variables. P represents for pressure, V represents for volume, 1/3 is a numerical constant. We're going to see how this constant come into action. M in this case represents the mass of one gas particle. I'm using the term particle because it could be used for atom or molecule, either one. Capital N in this case represents the total number of gas particles, plural. Total number of gas particles can be also found using the expression n can be given by small n multiplied by Avogadro's constant. Small n usually represents mole number. এই জিনিসটা তো বুঝো মোল নাম্বারের কনভার্সনটা বলবান?
Yes, sir.
For those who have a bit of a confusion about the mole number, let me help you understand it in a very easy form. Mole number is basically a way to express how many. For example, a pair means 2, a dozen means 12, a century is a alternative for 100. So similarly, a mole is a group is an amount of number, that how many of an object, and that is the Avogadro's constant. 1 mole means 6.02 × 10⁻23 of one specimen. So that many gives us 1 mole. So for example, if you have that many sand particles, you would have 1 mole sand. If you had that many carbon molecules, you would have carbon atoms, you would have 1 mole carbon. If you had that many O2 molecules, you would have 1 mole oxygen gas or O2 gas and 2 mole oxygen atoms. So that's like it. So if you have n mole of gas within a certain container, if you multiply that mole number with the Avogadro's constant, which is basically how many in 1 mole, you get the total number of gas molecules within that container. And c square is the mean square velocity of the particles. So we're going to derive this equation with appropriate process. So the way it goes, there's a very keen observation that you have to understand for this derivation, which I'll help you to understand. Let's say this is a cube box. It has L dimensions on all sides, although it's not appearing to be a cube because essentially it is hand drawn. So then let's say the length of this cubic box is L. At any point of time, any particle is gonna have velocity which can lead to all 3 different directions. So let me give you a bit of an idea of what this means. Let's say if you have a vector quantity that is to be divided into 2 axes, let's say x-axis and y-axis. This is a vector quantity. Let's say this is C. Then you can have the horizontal component Cx, which is going to be this much. You can have the vertical component, which is going to be Cy, which is this much. This is a division of vector quantity in 2 dimensions. Similarly, a vector quantity can be divided into 3-dimensional space as well, which is a bit difficult for me to draw over here. So I'm going to try to look out for some no. So this is the part that I want you to understand. Have a look at this figure. This is a nice figure. So in this figure, in this direction we have x-axis, in this direction we have y-axis, and this is the z-axis. So this is a 3-dimensional axis system. If we have a certain vector that goes in the 3-dimensional direction, which is easy for you to understand, if you just try to look at the corner of your room, bottom corner of your room, and try to visualize 2 of the horizontal borders as x-axis and y-axis, and the vertical border as the z-axis. And if you consider any specific location at the middle of the room, anywhere, and try to imagine a straight line from that corner of the room to that aimed point of yours, that line will have 3 different segments by which it can be expressed. So along the x-axis we have the horizontal component, which is the ax. Along the y-axis we have the y component, which is ay, and along the vertical component we have the vertical component, which is az. So the sum of ax plus ay plus az can give you the a vectors. This is how a 3-dimensional vector actually come into existence. For example, if I try to show you this for a 3-dimensional situation for which is scaled, let's say this coordinate over here is written as 2, 3, 5. So 2 on the this axis, 3 on this axis, and 5 on the vertical axis. So this is a 3-dimensional coordinate, which is just an extrapolation of the 2-dimensional scenarios. So that's how we mentioned for 3-dimensional scenarios. and there can be a lot more other figures over here which can prove to be pretty interesting, but I'm not going to get into that. I'm not definitely going to show discuss the idea of unit vectors with you right now, so I'm not picking up the other pictures. Unit vector is an amazing thing. It can help solve a lot of mathematical problems in far too easy version. So if we try to represent that thing in a three-dimensional scenario, let's say at any point of time, if a certain particle, let me draw the three axes maybe. Let's say this is our x, y, and z. If a certain particle has a velocity vector that is represented, let's say, like this. Let's say like this. So what this would mean that if I try to plot in within this plane with appropriate angles and everything, so this is the part which is gonna be, let's say this is the c vector, so this would be our cx component, this part would be our cy component, and this part over here, which is basically equal to this dotted line, would be our cz component. So I can express that this speed can be written as cx plus cy plus cz. All of these three components can make up the resultant or the main velocity of the particle. Now, for the sake of simplicity, for the case of an ideal scenario, we're gonna assume one thing. Should I say, because all the particles which we have over here, they're all stuck within a cubic volume, and they're all moving around in this three-dimensional space. On an average, because the particles are not going anywhere, on an average, we can consider that the numerical value, average value for this cx, for this cy, and the cz, the value of these three quantities should be equal, because this is a cubic box and the particles are not actually going anywhere. Can you appreciate this? Let me help you realize this thing. Let's say if there are, let's say, 10 particles, and the 10 particles are stuck within this L dimensioned cubic box, and they're not going anywhere, which means at any point of time, the total amount of their horizontal movement, the total amount of all of their vertical movement, the total amount of all of their z-axis movement should be approximately equal, because the sum of all of those movements should ultimately result in 0, this equation. And because the particles are practically stuck within, which means their individual components should be equal. Can you appreciate that? That they're not going anywhere. So all the particles should have the same amount of movement, because the length of the cubic box is same in all directions. So this is very important. What can I say? Concept that we have to appreciate. So all of these individual components for one gas particle should be approximately equal. In this case, we're going to use exactly equal, because that's what it's going to help us for the whole upcoming process. So in other words, I can write that if I replace this expression over here for the case of value, that cx, I mean the value of c, only c, can be written as 3 times the value of one dimension speed, or the exclusive value of cx can be written as 1/3 of the magnitude of the total velocity, because we just added this all together. This is basically what the 1/3 is going to come up in our upcoming derivation process. So the next part is actually quite simple. Let's say we have a gaseous particle which is currently located on the very left border and is about to start its journey along the x-axis towards this direction. So let's say in this case, this is the x-axis. So let's say it starts with the speed cx, covers this total length L, does a bump within this wall, and usually goes back all the way up to here before reaching up to the starting position. So within this part, the total amount of distance it covered is 2L. And let's say this total journey, starting from here all the way bumping and eventually going back, let's say it takes an amount of time t. this would be equals to horizontal distance. Hold up. আমি এখানে একটা জিনিস ভুলে গেছি। আচ্ছা হ্যাঁ সরি ভুল লিখছি আমি, মাই ব্যাড। এখান থেকে দেখো, let's say this is our side 1 on the left side. Let me zoom in. This is our side 1, this is our side 2. So the velocity of the horizontal component velocity of the particle, which has a mass of m, towards right is considered positive cx and towards left is considered to be minus cx. So let in a cubic container of side length L, there are n ideal gas particles, each with mass m. At any instant, the particle is moving from surface 1 towards surface 2 with the velocity cx. It collides elastically with side 2 and comes back to side 1 with velocity minus cx. It is our scenario. So in this collision process, what would be the change in momentum? The change of momentum would be delta p m into minus cx minus m into cx. So final momentum minus initial momentum, this gives you minus 2 mcx. This is the change in momentum. Now comes the part between two collisions with side 2, the gas particle covers 2l distance. Now this is the important bit. Between two collisions with side 2, the gas particles have to cover 2l distance. Why? Try to visualize this. Actually was discussing over here that the particle started from here and bumped into here and eventually went over here, but for the note we are considering 2 is the starting process, which is perfectly all right. So let's change the perspective a little bit. Let's say the particle starts its journey from wall 2. Sorry, no, I messed up. Let's say the particle starts from side 1, collides with particle 2, side 2, and eventually goes back to 1. So between two collisions, if the particle only moves horizontally, try to visualize that. If the particle only moves horizontally, how much time would it take to have in between two collisions with one side? So let's say it starts from here, goes all the way over here, and eventually comes back over here. So from side 2 going all the way to 1 and coming all the way back to 2. So between two collisions with one side, it takes some time. How much time is that? Let's say that time is t. So every collision with wall 2 takes t time. I mean, between two collisions you have t time, which means every collision takes t time. Do you understand this part? What I'm trying to mean is this. Let me draw this for you. Maybe let's say this is our surface 1. Let's say this is our surface 2. The particle is bumping left and right, left and right, left and right. It's bumping left and right. So let's say at one point of time when the particle actually bumps, it starts its journey from here, bumps into here, and eventually comes back into here. That's basically one cycle of hit. So to hit this surface 1 and to reach to the same starting position, the particle should start from wall 1 and eventually cover all this distance and eventually go back all the way over here. That's practically one bounce with the wall 1. For the second bounce, it should happen once again. For the third bounce, it should happen once again, which means for every bounce it makes with the wall 2, it has to cover this in between distance twice, going forward and then coming backward once again. Does it make sense? Boltzmann. For one bounce, the particle has to cover the L length twice. That's pretty much where this time information is coming by. Have a look. Between two collisions with side 2, the gas particle covers 2l distance. So the time between two collisions should be given by distance over speed, which is a very simple equation for time, which can be written as 2l divided by cx. This time expression will become useful just a little bit after. Now comes it. The collision that this particle does with wall 2 will exert some force. Force can be measured in terms of change of momentum divided by time. So delta p divided by time. We just calculated that the delta p is given by minus 2 mcx divided by time. Time is this expression. So 12 by cx. So 2 and 2 crosses out. We get minus mcx square divided by L. Then comes this expression. In the container, the particles actually move in all directions. Since all particles are identical, statistically we can say cx equals to cy equals to cz. And the vector quantity c is equals to cx vector plus cy vector plus cz vector. That's the part that I just showed you a bit earlier. By Pythagoras theorem, c square equals to cx square plus cy square plus cz square. Actually, I wrote it wrong. In this drawing board, I wrote this equation wrong. My bad. This is okay. This is wrong. I messed up. My bad. So this is the vector equation. So if from this vector equation, we can write that if we use Pythagorean formula, have a look over here, we can write that c square equals to cx square plus cy plus cz square. If you wonder where is that coming from, is basically coming from this consideration of the three-dimensional vectors. Have a look. In this case, let me zoom in so that I can write bigger. In this case, I'm going to go piece by piece. This is cx side. So I can also consider this one as cx as well. So I'm going to write cx over here. Let me use green. If I draw one diagonal over here, you have to understand that this is actually a right angle, because this is an axis, this is a component. This is actually a right angle. So on this right angle side, this is the cx side, this is the cy side. So what would be the value of this? Root over of cx square plus cy square. ঠিক না? By Pythagoras.
Yes, sir.
ঠিক আছে? Now have a look at this triangle. Have a look at this big triangle that is comprised with C and this diagonal, which has an 90 degree right over here, but this is the hypotenuse. This side is root over 6 square plus cy square, and this side is cz. So if I apply Pythagoras over here, I can write c square, which is the square of the hypotenuse, should be equals to side square plus side square. So which ultimately gives us c square equals to cx square plus cy square plus cz square. That's the expression for the hypotenuse of a three-dimensional vector. It's basically the square component added together. In this equation, if we now replace this logic that cx, cy, and cz all should be equal, we can pretty much come up with, I'm going to write this a bit lower. Let's zoom out. I'm going to bring up this equation over here. So I can write c square can be written as cx square plus cx square plus cx square. I'm replacing the cy and cz with cx only because I derived the earlier example for a horizontally moving particle. So that's why I want to express this in terms of cx. And that gives me c square equals to 3 times cx squared, which gives us that 6 square should be equals to 1/3 of c square in terms of value, which we're about to replace over here. So this is what we're getting. By Pythagoras' theorem, c square, which is the mean square velocity, equals to cx square plus cy square plus cz square, which we are replacing with these values. So we're getting cx square equals to 1/3 of the mean square velocity. Cx square equals to 1/3 mean square velocity. Here we had a cx square over here. We're going to replace this expression right up over there. So what do we get? এরপরে আর লেখা নাই, আচ্ছা এখানে আমার পেজ একটু ওলটপালট হয়েছে বলবান। এই পেজের পরে হবে হচ্ছে এইটা ক্যালকুলেশন কন্টিনিউশন, আর এই পেজটা হবে তারপরে। সো আই মেসড আপ আ লিটল বিট। বুঝছো? তুমি একটু নোটস দেখো তো, পেজ নাম্বার 7 আর 9 এর লোকেশনটা একটু ওলটপালট আছে। সো 6 এর পরে আমরা ডিরেক্টলি এইটা চলে আসলাম। সো এখানে আমরা এই 1/3 c স্কয়ারটাকে রিপ্লেস করছি, -m এর জায়গায় আছে, l এর জায়গায় আছে, and that way we get the force exerted by one particle would be given by m into -m into 1/3 c square divided by l. So this was the force exerted by one particle. So if we have n particles within the container, force exerted by n particle should be this whole thing multiplied by n. Pressure exerted by n particles should be given by, pressure is given by এখানে একটা করে s লেখা আছে because whenever we are going for multiple we should use plural. ওজন্য এখানে একটা করে s লেখা আছে. This s is not a variable, this is representing the s for particles, ওই plural এর s. Don't mess up this s for a variable name. So pressure exerted by n particles is given by F divided by A, which is force over pressure area. So P equals to mn 1/3 c square divided by L, which is this whole expression, divided by L square. Pressure is a tensor, so minus sign is omitted. এখানে আমরা মাইনাস সাইন কনসিডার করতেছি না because pressure is actually considered as a tensor, which for your level you can consider it to be a scalar because tensor is not taught at your level. So since it's a scalar quantity, we are simply obliterating the minus sign. এখন আমাদের মাইনাস সাইন নিয়ে বদার করার দরকার নেই. So now we're gonna mathematically make this thing a bit more valid. So PV B equals to mn 1/3 c squared divided by L cube. L square and L multiplied gives you L cube. L cube is basically volume. So on the top we are getting 1/3 mn c squared. On the bottom we get V. If we do the cross multiplication, we get PV equals to 1/3 mn c squared. This equation does not have any name of its own as far as I know, but it's a very helpful and required equation which can lead to a lot of multiple other derivation as well. এইটার পুরো ডেরিভেশনের প্রসেসটা তোমাদের মুখস্থ করা লাগবে না. You don't need to memorize this or you don't have to remember this as well, but you need to understand how this equation came into being. That we considered the motion to be statistically uniform. That's why we could replace Cx, Cy, and Cz to be equal to each other. That's one part that you have to understand. And then the time it takes for consecutive collision with one side is given by 12 by Cx. That expression. These two are the fundamental bricks towards this whole derivation. So you understand this part, that's good enough. You don't have to remember the total procedure. Further investigation, we know PV equals to 1/3 nRT. We just derived PV equals to 1/3 mn c square. Now you can do a bit more, a couple of other things. What we have over here is that okay, next thing that we have over here is average kinetic energy of one molecule is given by half mc squared. Now this is the expression for average kinetic energy of one molecule. We have to use the word average because we are using the mean square velocity, which is the average square velocity of all the particles. That's why you have to use the word average k of one molecule. You cannot write k of one molecule because it is nearly impossible to measure the k of one molecule at any given time. You have to physically observe one molecule's motion. So rather we write average k of one molecule is half mc square. So now we are going to equate these two parts and try to somehow bring about this expression within our equation, because we want to bring out the average k of one molecule within our expression. So this is what is happening. nRT equals to 1/3 mc squared. Equating these two expressions, nRT equals to 1/3 mc squared. N, this is the mole number, is expressed as n over Na. Number of molecules divided by Avogadro's constant. RT equals to 1/3 mc square. Now we are dividing the n on both sides. N crosses out. Na is Avogadro's constant, and then we get R divided by Na multiplied by T equals to 1/3 mc square. This R divided by Na is called another constant, which is called the Boltzmann constant. Boltzmann constant is actually pretty interesting. Have a look. What was R? R was the molar gas constant. It was defined as joule per mole per Kelvin. Joule per mole per Kelvin. So how much energy is required to increase one mole's gas's temperature by 1 Kelvin is molar gas constant. Boltzmann constant is basically that number divided by Avogadro's constant. So basically Boltzmann constant is how much energy is required to increase the temperature of one particle by 1 Kelvin. You're dividing that joule amount over Avogadro's number of particles. So Boltzmann constant is given by R divided by Na. So we are replacing that R by Na into K. K is the Boltzmann constant symbol. So K into capital T gives you this whole thing. Now we are bringing about some change because we want to introduce the half mc square within this expression. So we are writing half mc square because we want to have that, and we are writing the compensating fraction on the right side because we had 1/3. So the 3 goes at the bottom, and because we wrote an extra half over here, the 2 goes on the top. So the total product of this whole thing would essentially give you this expression. No big deal. Because we want to bring about the half mc square within the expression. So if I take the half mc square as K average, kinetic energy average, we get kinetic energy average into 2/3 equals to KT. Ultimately gives us that average kinetic energy of one gas particle. Important. Average kinetic energy of one gas particle is given by 3/2 KT. 3/2 into KT. Now, if you have a good look over here, 3/2 K, this is basically a constant. 3/2 is a numerical constant. It's just a number. K is a Boltzmann constant, which means the product of these two things will also be constant, which ultimately gives us kinetic energy of any average kinetic energy of a gas particle is directly proportional to the absolute temperature or Kelvin temperature of the gas. Ultimately leads up the equation information that I told you at the beginning of the class, that particles kinetic energy is exclusively dictated by their temperature, nothing else. If you have a high temperature, particles will have a higher average kinetic energy. If you have a lower temperature, particles are going to have a lower average kinetic energy. It is very important to mention the word average in every single case. Students make this mistake the most often in the answers of thermal energy questions. They don't write the word average. You cannot write kinetic energy of molecules. You cannot write kinetic energy of one molecule. That would be even wrong, more wrong. You have to write average kinetic energy of the molecules, because that's the way it works. The reason is very important for the average word to be used, because it is important that this part that we wrote over here, have a look over here, that this part, have a look. Statistically, Cx equals to Cy equals to Cz. This word is very important. Statistically means that we can exclusively apply this logic for a large number of particles where generalization can be applied. For example, I mean, if I want to give you an example for statistical data, if it is observed that for a certain country the population is not changing for a duration of 10 years, this does not actually mean that all the people are undead and they are all sterile. Rather, it means that the total number of people born and total number of people dead over that duration of 10 years were exactly equal. But this approximation might not be exactly applicable for a single family. In one family there can be less death and more born kids. In another family there can be less born kids and more born kids and less deaths, or vice versa. But if you consider this whole expression for the entire country, you might have an equilibrium scenario. So statistical data to be applied, one of the key requirement for, in any case, for statistics to be applied or approximation to be applied, is that you need to have a big number of specimen. You need to have a certain number of people or certain number of specimens so that you can apply a statistical approach. For a certain amount of gas, it is possible, because we are talking about Avogadro's constant multiplied by mole number of gas molecules, which is a huge number. But if you're only doing this experiment for, let's say, 10, 12 particles, this wouldn't be applied. So this word statistic is very important. I actually talked a little bit about 10 molecules at one part of my lecture, but that's actually wrong. We cannot do this approximation for a very small number of particles. There has to be a huge number of particles so that we can apply this approximation of Cx equals to Cy equals to Cz, which is a statistical bit. Moving back to the mathematical expression. So here we get even more. So furthermore, PV equals to 1/3 mc square. Now, if you have a look at this expression, m into n, m is the mass of one gas particle, and n is the total number of gas particles. So which means this product basically means the total mass of the gas. Mass of one particle multiplied by number of particles gives you the total mass of the gas. Pretty basic. So if I bring the V at the bottom, we can write P equals to 1/3 total mass of the gas divided by volume. I didn't use any symbol over here because I didn't want to confuse up the kids. So I wrote the whole thing in words. Total mass of the gas divided by volume, and total mass divided by total volume basically gives you the density. So pressure of a certain gas can be also expressed as P equals to 1/3 rho C squared, which basically means density of the gas. So these square equations that you can see over here, which I put in the box, would come in very helpful for the mathematical calculation. Now you might wonder, there are so many different expressions. How are we going to remember all this? You don't have to memorize them all at once in a single sitting. Don't do that. Don't even try to do that. Keep the worksheet at hand. Keep the formula paper at hand. Any single time you need to use a formula, go back to your theory part. Find out that formula and copy it from there and use it to your equation. Keep doing that. Your brain will pick up the necessary information that you are using repeatedly as stored information within your brain. Allow your brain to do the job rather than you doing the job. So just use the formula from your source, look up from there and use it from there, and that way you will be able to remember it. Don't spend some exclusive time to actually memorize this formula. Not recommended. All right. Beyond this point, what we have is the ideal gas assumptions. Ideal gas assumptions are actually pretty dumb. তোমাদের কি সবারই কেমিস্ট্রি আছে? কেমিস্ট্রি নাই এমন কেউ আছো? Anyone? No. So তোমরা ideal gas assumption already কেমিস্ট্রিতে পড়ছো না?
Yes, sir.
There are a good number of assumptions over here, and these things are explained over here as well. There is a certain table for this, I think, in your book as well. If I go for your book, ideal gas assumptions, do we have that? The meaning of temperature is very important. You should read this from your book. What do we mean by that? It's an important concept. And all of those, you see, all of the state change graphs are also within this part of the syllabus, because these parts are also going to be needed. I didn't go through this part because this was done in our O levels. There's going to be a small recap for this thing. After a while, I'm going to show it to you. No, don't worry. তোমাদের বইয়ে তো আইডিয়াল গ্যাস ল ছিল, এটা গেল কই? আচ্ছা, আইডিয়াল গ্যাস পরের চ্যাপ্টারে, না ব্যাড। First molecules. Acha, this is also another part, another thing. If in your question, in any case, the question asks you to draw a possible path for a particle to move with multiple different collisions. The particles, acha, এটা তো আইডিয়াল গ্যাসের ডেফিনিশন আসবে, বলতেছি দাঁড়াও। This table that I was talking about, table 22.1, which is on page number 353 in the second edition of your course book. This is basically something that I made the students write in the class note, right over here, right over here. So that's basically it. I just made them write this whole thing. The ideal gas assumptions are actually pretty simple, but there are a couple of things that we really need to understand in detail. Can you read this thing with this font size? Is it legible?
Yes, sir.
Achha. First assumption is that a gas contains a very large number of particles out of some molecules. This means a small cube of air can have as many as 10 to the power 20 molecules because of the Avogadro's constant. We need so many molecules so that we can apply statistical approach towards their behavior. That's a very important thing. So whenever we're talking about ideal gas equation, ideal gas motion, ideal gas assumption, and so on and so forth, we are talking about that we are handling with a amount of gas where there is large enough gas molecule so that we can apply statistical approach towards the behavior. We're not talking about 100, 200 molecules or 100, 200 particles. No. Then it says the forces between the particles are negligible except during collisions. Here they're using the word negligible. In for ideal case, we consider them to be 0. This basically means that if the particles attracted each other strongly over long distance, they would all tend to clump together in the middle of the container. The particle travel in straight lines between collisions. What it means is that whenever, if we have some big number of particles within a gas container, the particles will only exert force onto each other, or they will only experience force whenever they will undergo a collision. I'll say this again. Particles will only experience a force whenever they will undergo a collision, either with a neighboring particle or maybe with the container wall. But as long as they are not experiencing any collision, or they are moving in between two collisions, they will experience no force whatsoever, which means their motion will be perfectly unobstructed. This basically goes on to mean that the particles inherently within themselves don't have any attraction or repulsion forces. They are perfectly unaffected by neighboring particles, which means they don't have any intermolecular force. They will only experience a force whenever they will undergo a collision. Collision might be with themselves, collision might be with the container wall. No attraction or repulsion forces for the motion in between two collisions. Force will be only experienced exclusively when they undergo a collision. So bumping into each other, bumping into the container wall, force will be experienced. Moving in between one collision to another, there'll be no force experienced. That's the key idea for the second assumption. So this means about the particles travel in straight lines between collisions. This is what is very important. In any case, if you are asked to draw a possible movement of movement path of one gas particle within a container, you have to use a ruler. I mean, the motions can be shown. There was another figure right over here somewhere. There was a graph for this. So have a look over here. The motion of the gas particles can be drawn something like this. They can be overlapping, they can be intercrossing, but from one point of motion to another point of motion, I mean, whenever there will be collision, there will be a sudden change of direction. But from one point to another point, we cannot have curve. You can see over here that this part, I mean, this part actually looks like a curve, but it's not actually a curve. It's actually a combination of multiple different straight lines. So it's important, if you are trying to draw the motion of a particle, gas particle within a container, you have to use ruler. You have to use ruler. I cannot stress this enough. Students এই simple জিনিসটাতে অনেক মার্ক লুজ করে অনেক সময় because they don't use ruler. The third thing that we have is this. The volume of the particles is negligible compared to the volume occupied by the gas. In the ideal case scenario, we consider the volume of the gas particles is 0. Negligible is a bit more realistic term, but actually we mean it to be 0. What it means, the explanation that they have given is that when a liquid boils to become a gas, its particles become much further apart. Okay, much further apart. এই জিনিসটার physical meaning-টা তোমাদেরকে বলি, সেটা হচ্ছে the volume of the gas particles. Now, whenever I say volume of the gas particles, what I'm meaning is if all the particles were clumped together in the least possible volume, pretty much like the case for a solid. Try to think about it. If you have a cube of water molecules which was eventually boiled into steam, so the amount of volume that cube amount of water molecule is going to occupy as steam is going to be enormously big, like superbly huge. So the exclusive personal volume of the gas molecules themselves is negligibly small compared to the container inside volume of the container in which they are kept in. That's the key idea. Now, why is it important? Because we are for an ideal gas, we are considering the particles to be of 0 dimension. We're considering the gas particles to be particles. The key concept of a particle is that it has considerable mass, but it has 0 volume, which means it doesn't have any dimension, pretty much like a dot. So this is important for our mathematical approaches as well. Have a look over here. Let me show you another thing. Whenever we are considering this expression, the amount of time it takes between two collisions, we considered that the particle was covering 2L distance between two collisions. Remember, the particle was covering 2L distance, and 2L was the distance, was the length of the container. If the particle did have some dimension, if the particle did have some size, it would have covered less than 2L. If you wonder what do I mean by this, let me show you. This is the part where I show you that the particles are making collisions with the two walls. Let me just show you with one thing. We are considering the particles to have 0 dimension. That's why to move from one wall to another wall, they're covering 2L distance. They're covering L distance. So between consecutive collision with one wall, they are covering 2L distance. But if the particles did have size or measurable diameter, let's say this is the diameter of the particle, this is the diameter of the particle. To make collisions in between two walls, it would have moved from this position to this position. It means the total covered distance wouldn't be L. It should be L minus 2R, because it is starting to move from this position, ultimately moving to this position, which means it is moving slightly less than L, right? Do you get my point? The center of the particles wouldn't be moving by L distance. The center of the particles would be moving by 2R less of the L distance. But that's not the case by which we develop the equations for ideal gas. Ideal gas particles are considered to be of 0 volume, 0 dimension. So their personal volume is considered to be significantly smaller, negligible, sometimes 0, compared to the container volume. You have to understand all of these are ideal gas assumptions. Assumptions means they are a highly simplified scenario of a much complicated realistic case. Then Most of the time the particle moves in straight line at a constant velocity. The time of collision with another particle or with the container wall is negligible compared with the time between collisions. This is also important. It means that the duration of collision is extremely small compared to the time it takes to travel from one collision to the next. For a more extreme version, it takes 0 time. Now, mentioning a collision takes 0 time would imply that the force experienced is infinite. So we are not bringing about that complicacy over here. So we are using the term that the time it takes for the collision to happen is negligible compared to the duration, compared to the traveling time. So what this can be shown over here, let's say we have a particle that is going around in this way. So it is making one collision. It's starting from here, doing one collision over here, another collision over here, hitting the container wall over here, hitting the other container wall over here, another collision here, another collision here, another collision over here. So let's say it's moving in this path. The contact time between two objects, either two particles or one particle and the container wall, the contact time would be extremely small compared to the time it takes to move from one collision to another collision. So it will be small, like a huge scale. I mean, if I try to give you some physical example, maybe unrealistic physical example, let's say if the collision between two consecutive collision, if the time duration is, let's say, 1 hour, the duration of time it might take for the collision to happen might be in the microsecond level. So that much small. So very small, significantly small. If you wonder that why is that important, the reason it's important because we want the collision not to take significant time. Once again, because have a look, we considered that the particle was moving from here to here and back over here in a total time of t, and the particle didn't stop over here. That's the assumption that we made. If the particle does take some time to stop over here, or if the collision does take some significant time, then we would have to consider that time within our in-between collision as well, which we didn't, for the sake of simplicity. So for ideal gas particles, the collision duration is negligible, or can be said to be almost 0. The last expression, the collisions of particles with each other and with the container wall are perfectly elastic, so no kinetic energy is lost. Kinetic energy cannot be lost. The internal energy of the gas is the total kinetic energy of the particle. So if we have a certain amount of gas confined within a container, and the temperature of the container does not change over time, the total kinetic energy of all the particles has to remain constant, because we have just derived a bit earlier, average kinetic energy of the particles is directly proportional to temperature, absolute temperature, that is. So if the temperature of a certain gas amount is not changing, then their average kinetic energy should also be maintained, which means in every collision, either with themselves or with the container wall, no kinetic energy should be lost, which ultimately means that the collisions should be elastic. So এগুলো হচ্ছে আমাদের অল টুগেদার আইডিয়া। এটার পরে আমাদের আরো কিছু ছোটখাটো জিনিস আছে। ছোটখাটো জিনিসের মধ্যে একটা আছে হচ্ছে আইডিয়াল গ্যাসের অ্যাজাম্পশনগুলো আমরা দেখলাম। আচ্ছা, ছোটখাটো জিনিস বলতে এগুলো ছোটখাটো না, এটা হচ্ছে আমাদের ও লেভেলসের কিছু জিনিসপত্র আছে যেগুলোর রিক্যাপ আমাদের লাগবে, সেগুলো আমাদের যে এখানে লেখা আছে যে ও লেভেলসের কি কি জিনিসপত্র লাগবে, যে ইকুয়েশনস দ্যাট উই হ্যাভ ফর স্পেসিফিক ক্যাপাসিটি, দ্যাট উই হ্যাভ ফর লেটেন্ট হিট, মানে টোটাল হিটের যে ক্যালকুলেশন আমরা ও লেভেলসে শিখছি, কিউ গোস টু এমসি ডেল্টা থিটা, কিউ গোস টু এমএলএফ, কিউ গোস টু এমএলভি, এই ইকুয়েশনের অ্যাপ্লিকেশনগুলো আমাদের রিলেভেন্ট গ্রাফ বা রিলেভেন্ট ম্যাথমেটিক্যাল প্রবলেমের জন্য করা লাগবে, which are going to be a much more energy, much more information enriched and much more interesting scenarios. So sometimes it can lead to a little bit of critical thinking, which I'm going to help you with, but these thermal problems are actually quite interesting, and the basic is very simple as long as you understand them, and the maths are going to be fun if you can solve them well. That's pretty much it for today's class. I'm going to call it a day. নেক্সট ক্লাসে আমরা ওয়ার্কশিটে কিছু প্রবলেম সলভ করা শুরু করব এবং হচ্ছে তোমাদেরকে এই টপিকের কিছু ম্যাথস দেখাবো, and we will pick it up from there. Thank you very much. Assalamu alaikum.